Okay, so there's not too many of us online, but I will have to start the lecture anyway. So I'm going to just continue in fact, finish the crash course on differential geometry. Very quick review from yesterday. We were talking about various objects associated with the manifold. First, we talked about a slight twist on the term of manifold, so submanifold, which is part of another manifold, still a manifold. And we talked about manifolds with boundary, such as this one, which will be then locally diffeomorphic not to Rk, an open set in Rk, but an open set in the positive half space of Rk. All right. And then we looked at various examples of things that are manifolds with boundaries, such as a cylinder, a hemisphere, or things that are not manifolds with boundary, although when we take away their boundary points, they do become, as sets, they do become manifolds, such as this square without its boundary. Okay. Then we talked about the tangent space. Tangent space, I'm sure you had intuition for that, and you may have seen this definition before, but I just wanted to fix what it is. It's basically you can get it at each point by taking the range of the derivative of the local parametrization for the manifold. That will be a linear mapping, and that will be just maps from the sort of the modeling space for the manifold into the tangent space of the ambient space at that point. So that you can take the ambient space and make a mini-me copy of that and just place it here, and that will be the tangent space of the ambient space at that point, and you will be generating vectors there using the linearized parametrization phi, and the span of those is the tangent space, okay? Then we talked about how you have a mapping between two manifolds. Then you can talk about the derivative of that mapping, which is a linear map that maps individual tangent spaces to each other. This will be important because think of this map as the flow map of a dynamical system that is, say, operating on an invariant manifold, which is, large and curvy, and it may have a tangent space here, and this point flows on the invariant manifold, and it ends up being here. So the manifold has a tangent space there. How are those tangent spaces related? And they are in fact related. If this was the flow map that advected this bit of the manifold into that bit, then in fact its derivative will be mapping this tangent space to that tangent space. So that will be an important consequence of what we were discussing yesterday. This is how you can define the derivative of a mapping between manifolds if you don't a priori know what that should be, but you know how to do calculus between Euclidean spaces and went through that. A very important concept is that of the tangent bundle, which pulls apart tangent spaces, because as they might seem right now, they are not independent linear entities, but maybe they might be intersecting each other. But this construct of, generally speaking, of a vector bundle or fiber bundle is a set of ordered pairs, which also notes the base point where you are, here or there. And then corresponding to that base point, it considers vectors that are sticking out of that base point and separates them. So basically, even though technically, if you take this literally, then the vector starting from this point pointing to that point, and that one starting from that point pointing to the same point, you might consider their outcome to be equal. But once you can introduce this construct of a tangent bundle, these two entities will never be equal because their base points are different, right? So this enables you to do basically undisturbed calculus on individual tangent spaces without having to worry about a double representation. These are called the fibers of the bundle. And we just talked about the fact that locally, every tangent bundle is trivial, meaning that locally you can just think of the tangent bundle, say, of this piece of manifold as an open set in the manifold, okay, and basically cross whatever the dimension of the tangent bundle is, right? So locally it would be sort of a cylindrical domain. That happens to be true globally. For the circle, its tangent bundle is the cylinder, but generally speaking, that's not true. So tangent bundles of even nice manifolds such as the sphere are not globally trivial. They're not globally products. Any question on this? Recording is running as far as I can tell. Let me check. Yeah, okay. No questions. That I just want to finish up very quickly with basically 3 notions that we will still need, and then really then started on normally hyperbolic invariant manifold. So this will be just basically 3 definitions that I'm going to add to the mix. The first definition is, I think, very intuitive. Once you know how to talk about the tangent space, you can talk about the normal space locally of a manifold. So it's really what it is. It's basically, it's really what you think. It's a generalization of a normal vector, which we all know and love, right? Except that if a manifold is a fairly low dimension in an ambient space, then you can set up a lot of normal vectors, and they together form a linear space. Well, that's just the definition of the normal space. So if our ambient space here is as it has been is Rn, and I have a manifold living in that space, then once I have the tangent space of the manifold defined, which we have already done, right? So this would be the tangent space at the point x. So this is your x, and this is the tangent space to the manifold at m. Then the normal space is just the combination, the span of all the possible remaining directions, given normal directions, that is. Given the constraints of my picture, I will only be able to draw one direction, but I think of this, generally speaking, as a whole linear subspace, which generally doesn't have dimension 1. So the notation for that will be normal based at x to the manifold xm, right? So if I want a definition, then the nxm will be the set of vectors. So where do these vectors live to begin with before I say what they do? Well, they don't live in the tangent space, okay? They don't live in the normal space because I'm just defining the normal space. So what would be the notion for me to say, well, I'm selecting candidate vectors from a linear space. I'm not selecting them from Rn, right? Because they all stick out from here. They have to stick out from here. But at this point, I want to be pretty general. And before I say what they are, I want to allow all these guys as candidates for the normal space. So that means that I really have to locally place my Rn here and shift it here, right? This one there, and allow for all the vectors to be sticking out of there. So that means that this has to be taken, all these candidate vectors must live in the tangent space of Rn to Rn to itself at the point x. Okay, so that's sort of the candidate. But then I want to restrict and I want to say what they are. V has to be orthogonal to Txm. Okay, and for that orthogonality, you could say, how do I define that? That can be really tricky. Not really, because that's one of the advantages of working in this Euclidean space, that I have a notion of orthogonality, basically inner product, right? And this Euclidean space, you have the classic Euclidean inner product. So what you can just do is say that the vector is tangent to a linear space if the inner product of that vector with any vector in that space is 0, right? So that shouldn't be too difficult. And I'll just indicate that this is tangent there. So that at that point, that's well defined. So if we want to talk about the dimension of this linear space, that shouldn't be too difficult, because I basically need to look at how many linearly independent directions I can think of that I can erect to this tangent space. And we know that if the ambient space has just one more dimension as the manifold, so we basically have what we call a hypersurface in the manifold, then I have one normal to that. So dimension would be 1. However, if I have more dimensions, I start stacking up the dimensions, then I can add more to those. And the linear combination of 2 normals is also normal, right? Because if you feed that into an inner product, a linear combination of 2 normals with any vector on the tangent space will still vanish. You work out the details of that inner product. So it's really the codimension that matters, right? It's the codimension of the manifold within the space that determines the dimension of the tangent space. So I take the dimension of the ambient space and I subtract the dimension of the manifold, and that will be locally the dimension of the normal space, right? That's not surprising. And again, it checks out when you have just one dimension difference between the two. And in terms of linear algebra notation, one can also point out that if you take the tangent space to M locally, then it will have an orthogonal direct sum with the local normal space. And that orthogonal direct sum just adds up to the local little copy of Rn over there, right? That's all just definitions. Now, there's one interesting thing with compared to everything we've been looking at. We have been looking at intrinsic properties, right? To characterize the manifold in intrinsic matter as much as it was possible. And certainly we found that to be the case for the tangent space. Remember that I told you it doesn't matter where the manifold live, the tangent space will be intrinsic. Not only is it independent of the parametrization, but as a geometric object, it's independent of the ambient space. The little example being, remember the circle being placed on the table or being placed in R3, the tangent vectors of the circle are always the same. It doesn't matter where you put it. And you could say, well, then that's probably a general phenomenon, right? Because anything I associated with the manifold, which is meaningful, will just be intrinsic to the manifold. But here's already an example in which that's not the case, all right? So the dimension, the first indication that this is not independent, this construct from the ambient space is right here. Because when I count its dimension, it's heavily influenced by the dimension of the ambient space, okay? So that's a first indication already, and I'm going to state that so that note that unlike the tangent space, NXM depends on the ambient space quite heavily. And just going back to a circle example, if I take my classic circle as a manifold, right? And so this is S1, the circle, and I view it within a two-dimensional space. So this is R2, and R2 contains S1 in this case. Then what is the normal space at any given point? So I pick my point X here, and it's not hard to visualize what the normal space is. The tangent space is here. My color for that, the international color of tangent spaces is yellow, orange, sorry. So that would be TXM, right? And the rule is you just need to erect this, need to identify the subspace that's normal to it. So this is your NXM, right? And the dimension of this NXM is 1, because that's the codimension of the manifold in the space, right? However, if you now take the same S1, which I can't guarantee to be visually the same, but conceptually the same it will be, right? That's pretty close, right? So this is S1, but now I embed it, I consider it to be part of R3. So in this three-dimensional space, again, I take a point there and note that the fact that I pass to a different space doesn't change the tangent space at all. Still the same good old tangent space right here. So that's TXM. But what is the normal space now? Well, I have two complementary directions, two linearly independent. I have many of those, but two linearly independent ones. So I have a whole normal plane here, right? Which came out to be a circle, but it's unintended. Okay, so that's now the normal space. Okay, so it's a whole different game because all these are normal vectors, all of them. So clearly very much depends on the space. So it's not intrinsic anymore to the manifold as the tangent space was. Now again, I introduced these linear objects for a reason. I want to do calculus on them, and I don't want them to bother each other. In the tangent space, bothering each other was pretty obvious because inevitably two nearby tangent spaces would intersect. That's not so obvious with the normal spaces, because if you think of a plane, then, or you think of just of a circle, and then they point all outwards, right? And they don't seem to intersect. But if you look at the parts that point inwards, those already intersect. So it also makes sense to pull the normal spaces apart. And that leads to the idea of the normal bundle. And constructing the normal bundle follows the general idea of a vector bundle again. So it's a collection of normal spaces labeled by their base points. Okay, so the notation would be NM, and it's again a collection of vectors. First, I know the base point, and then I add the vector. So any element in the normal bundle, as in any bundle, will have two coordinates, so to speak, except that, mind you, these are not coordinates ever. I never actually introduced a coordinate. X is here just labeling a point geometrically, and V is labeling a vector. So a coordinate system is not used in this. Only spaces are used. And the pairing is such that X is taken from M, and the connection is that V is always taken from the normal space right there, okay? And that pulls out away, again, normal spaces so that they won't intersect. So removes overlap. You know, this is the type of thing we don't want to even think about, that this is one normal here, and this is another normal there. And then they somehow intersect in principle. So how do I handle that, right? So that's now eliminated once so basically this idea is that they really don't know anything about each other, right? A normal space erected at this point, doesn't matter how it stands, doesn't matter the other one, it's just completely oblivious to any other normal space. It's an entity by itself. It would not know about any intersection that I, as an observer, would perceive between them. Because the minute you have two different base points, there's no way that any two elements, you don't even have to check the second element. There's no way that two elements of that would be equal, right? You only have to check that. So what is the dimension of this object? Now, as with any vector bundle, I have this actually turns out to be a manifold. So this is also a manifold by itself. And if you accept that, then why is that likely? Well, because I already have a parameterization for this entity here, right? Because that's always taken from the manifold. And this other one is just a linear space. So I can have a parameterization for that as well. It will be an X-dependent parameterization unless I have a trivial bundle. Again, generally speaking, the normal bundle is not trivial. So I'm not saying that automatically I can use the same parameterization, but I can certainly hope to be able to construct a parameterization because this part is taken from linear space, and this has already been found a manifold. If that's the case, then I have, k degrees of freedom here, because that's how many parameters I need to parameterize the manifold. And then individually and each and every subspace, I will have n minus k degrees of freedom, right? Because that's the dimension of the normal space. So if I add those up, the dimension of the tangent bundle should be, first I have k dimensions, that takes care of this. But once I have fixed that, then I have still n minus k degrees of freedom that I need to parameterize. So that gives the really interesting result, which really makes it entirely obvious, excuse me, that even as I make an attempt to work nicely and remove potential intersections among normal spaces, there's that intrinsic dependence on the ambient space, which is now unapologetic because it only depends on the ambient space. So once you throw in the normal bundle construct, remember, just look at this. The dependence on the manifold, in terms of dimension at least, has completely disappeared. So that when you ask what's the dimension of the normal bundle, it's just the ambient space. No, in terms of that, the dimension from M has disappeared. Of course, there's dependence on the manifold. That's why I'm keeping in the M there. And sure enough, this is the first component of the ordered pair is taken from M, and the second one is taken from the normal space. So M is all over the place, but fundamentally the dependence on the ambient space is very heavy because of that dimension. And the last object I want to define would be more of a generalization, which we also need, of the bundle concept for M. So that would be just a general subbundle of the normal bundle. Because I will be, so, the normal bundle, again, at each point you have a normal space. And I want to have the freedom to concentrate on distinguished subspaces within the normal space that actually will be attached to trajectories as they travel on the manifold. They will be distinguished because it turns out because different dynamics will be taking place along those. And I have to have just the general machinery to do that. You will see that shortly why I need that machinery. So that just in words first. So this would be an X dependent, which is location dependent, right? Not coordinate. Nothing is in coordinates here. X just refers to points at this point along the manifold. So it's an X dependent family of subspaces in the taken from the local normal space, right? So at each and every point we have, sorry, I wrote tangent, but it's normal. And each and every point we have the normal space, and now I'm passing to some subspace of that at each and every point. Generally speaking, my choice of that subspace will also depend on the location, right? It will not be some sort of magic orientation necessarily that I want to pick in each and every one of them. I want to, reserve the freedom to have an X-dependent construct. But here comes the important thing, is that is smooth in X. So in other words, in terms of the locational dependence of these subspaces has to be smooth. Okay, I cannot just arbitrarily, assign. I could, but it's not. It wouldn't be terribly useful because again, I wouldn't be able to do calculus differentiation along these subspaces. So I want to assign them in a meaningful way so that they vary smoothly. That immediately implies, by the way, that the smoothness is there also that dimension cannot be flip-flopping. It's gonna be that subspace at each point will have the same dimension. Okay, so a formal definition would be that I still consider pairs such that X is taken from the manifold and V is taken as an element of some subspace which depends on X. Okay, and that subspace is a subset of the normal space there, and this assignment of the subspace as a dependence on X is just gonna be some sort of, let's pick it, smoothness or bigger than or equal to 0. So S as a function of the location is smooth. An immediate consequence of that smoothness is that the dimension of S of X, okay, as I consider that for all X values in M equals constant. It cannot be changing. So that's in fact just to make sure that it actually follows from this here, right? From that smoothness. So it cannot be jumping around. If I started out with a one-dimensional subspace, it may be rotating nicely, smoothly, okay, as I move along X, but it cannot turn into a two-dimensional subspace because then the function that defines the subspace, whatever function I choose within the normal space, would have a non-smoothness problem all of a sudden, right? So the picture then one should have in mind is that if this is the manifold M, okay, and this is, say, the first point in manifold X1, and you might have an X2 here, and you might have a point X3 as I'm moving along. Then if I set up then I will need to consider the local normal spaces. For me to have an example. So these are local normal spaces. This is NX1M, NX2M, and NX3M. Of course, here M is one-dimensional because I can't draw higher dimensions, but there's nothing that would intrinsically connect these 3 points when I start looking at higher dimensional manifolds, right? There's no curve necessarily. They could be at any point, okay? And the idea is that I will make local assignments of subspaces within these. So I might start with something like this here. So this will be my S of X1, and then, you know, it might be something like that here, S of X2, and something like that here, S of X3. But it might sound like or look like that I have designated these arbitrarily. So I will have to say what I was doing in between. How were they varying from this position to that position? And this sort of cartoon would show you that their envelope has to be varying smoothly. I make an attempt. So let them go there, because it has really turned around. And then these envelopes, and we are like this, right? So the individual subspaces, as I move along them, they don't change their dimension. As I move along any path, they would continuously deform. And they have turned around quite a bit here. So what's a good... well, for geometric effect. Anyway, I think I have a better picture in the notes, but perhaps you get the idea, right? In the notes, I sort of added something like this down here to show that this is this is turning, but I don't know if that helps here given the geometry. So I just leave it as it was. Point is that these are the if you then take a general point here, X, then this will be S of X there, right? It changes smoothly and has the same dimension. Again, in this context, we would call Xi is the base point of the fiber in this bundle, SX1, just to get that terminology. And again, there would be no intersection between fibers with different base points, even though in my picture that could happen, but excuse me, the same way as the normal spaces in my picture could intersect each other. But mind you, again, two different fibers know nothing about each other. They're not to be identified because once their base point differs, they are certainly two different entities within this bundle set. Okay, and that was the last thing I wanted to say. Obviously differential geometry is a huge subject, but these would be the notions that would just the minimal set of notions we would need to get started to discuss normally hyperbolic invariant manifolds. So before I do that, are there any questions on these notions? No questions? Then I move on to normally hyperbolic invariant manifolds. And for decades, there was no acronym for this, but then somebody had this great idea that this is a long term, so let's call it NIM. Actually, I think that it came to existence when people have really started seriously applying this in other fields. And I think it was the first appearance of NIM was in theoretical chemistry, where in these large phase spaces for chemical reactions, people use Hamiltonian systems and try to understand, what might block reactions, which would be a transition. A reaction would be a transition from one part of the phase space to the other, and what would be facilitating or blocking. And they started using these terms in those papers, and it just was too long. So somebody said that's going to be a NIM, and I think then that influenced the applied math literature, and also people have started calling it NIMs. And why had we not thought about that before? The setting which I'm going to discuss here is the simpler setting, which is finite dimensional and autonomous. There are extensions in both directions, the non-autonomous and also even infinite dimensional. But it's enough, I very much believe that it's enough to understand the basic ideas in the setting that I have here. So we have an autonomous dynamical system that is smooth. We will be assuming that existence of solutions is not an issue. Remember, just because it's smooth, it doesn't guarantee that by itself doesn't guarantee that you have local existence and uniqueness, but it doesn't guarantee global existence and uniqueness. And I have to assume now some sort of globality, because I don't want to be bothered by the fact that as I advect, initial conditions by the flow map, then all of a sudden I just blow up, that I don't want. Okay, so assume for now, global existence for simplicity. Uniqueness is not an issue because that I always have locally, so therefore I will have it globally. At no point can trajectories intersect once you're Lipschitz, and you're more than Lipschitz here because you're at least C1. Okay, so assume global existence. Now here comes the other assumption that actually I assume, and that makes my life much simpler than it is in practice, is that I assume that I know a manifold. So I know that I have in Rn, I have somehow found a k-dimensional compact invariant manifold, C1 manifold, I think, compact. No, that the invariance comes later. So because I want to be a bit more specific about the invariance, I just k-dimensional compact, and it's C1, at least C1 manifold with boundary. Mind you, that includes the case when the boundary is empty, but it's not a restriction. So possibly we have okay. But when the boundary is empty, I'm still maintaining that the manifold has to be compact, okay? So don't think of anything like a sheet, a nice open sheet with the boundary removed. That wouldn't work, because even though it doesn't have now any boundary, it would not be compact. So the boundaryless manifolds that come into play are invariant spheres, invariant tori, circles. So these are compact invariant manifolds without boundary, but they're compact. So they're not open sets. That will be important. Here comes now, I want to specify the type of, in dynamical systems, we tend to care about manifolds. In fact, that's the only reason why we should care about them, if they're invariant, okay? Which means that they themselves are built out of influential trajectories. And as a whole, they have an impact on other trajectories, either push them away or everybody's neutral relative to them. So nearby trajectories will pick up pretty much the shape of the manifold, or, and this is the most important case, is the manifold attracts all of them, because then actually offers a wonderful opportunity to understand the full dynamics in terms of a reduction to that manifold. And that's one of the main drivers behind the invariant manifold theory, is to to obtain a reduced representation of the dynamical system because I'm running to this attracting manifold anyway, right? So for longer term description of the system, it should be then enough to understand what happens on the manifold itself. You hear perhaps the term a lot, attractor. And if it's a lower dimensional attractor than the phase space, then this is basically your chance to have reduced dynamics. I'll talk about that later. So in all these cases, the manifold is invariant. And however, it's not, life is not as nice to have that invariance in general. You'll see in examples. So I have to qualify that a little bit. So instead of having just full invariance that you would have for a torus or a sphere that has no boundary, I have to deal with the fact that I have a boundary. And when I have a boundary, I may leave the manifold or I may come into the manifold through the boundary, okay? So I have to address that. I don't want both behaviors. For simplicity, I don't want people going in and out in forward time or backward time. That would lead to a mess. So I will restrict for now the notion of invariance to overflowing invariance, and that's what I will assume. So M naught is overflowing invariant. If this vector field that defines my dynamical system and basically tells me, right, it gives me immediately a tangent, an orientation for trajectories, I want that to be pointing outwards on the boundary of M naught strictly. So this is sort of a compact manifold with boundary. It's my picture in Rn. And the kind of behavior I want is consistently, I want the vector field to be pointing outside on the boundary. Now, what's the implication of that? The implication of that is that the right-hand side of the differential equation tells me instantaneously where the trajectory is going. If the right-hand side as a vector points outwards, which I leave to you to verify, I mean, once we have the notion of tangent space and most notably the normal space, and since this guy is a manifold by itself, then it will have a normal space at each and every point, right? And you can also define an outside direction if for no other reason, since you have always the local parameterization. So you will have, right, this will be a local open set in HK, which is diffeomorphic locally to this manifold. And to HK, you can always associate an external direction, right? And then you just map that appropriately with an expansion of that map. So that's a technicality that I trust you can imagine. I don't want to go into that, but you can always define an external normal direction. And once you have an external normal direction or set of normal directions to the boundary, you can simply take inner products of those external normal directions with the vector field that defines the dynamical system, and you can require that inner product to be to be positive, right? So if it's always a positive inner product with the outward pointing normals, then you can verify that at each and every point F points outside. So hopefully that, I don't need to go into that. At this point, it's enough to have just sort of a feeling for that. That's okay. What's not okay is this, that trajectories, so these would then imply, what are my trajectories? The trajectories would then go like this out. Always, strictly. And what's not okay, sorry, is to have behaviors that I can't quite control. So I don't want to have trajectories that do this. Sorry, a tangent to the boundary at some point. because I don't want to spend time on identifying what they're gonna do. Are they really gonna get out, or are they actually turning back? That would require a higher order analysis once the only thing I know is that right there, the right-hand side is tangent to the boundary, right? That I don't want. And I definitely don't want trajectories coming in when I require F naught to be invariant. So these are the cases that these are excluded. And just to give you an intuition why I'm being so picky, because I would like to make general statements about behaviors in a certain time direction, as it turns out to be important. So I will be looking at the flow map as it maps various entities. And if I get out of that manifold or get in, and I have to be then start worrying about individual trajectories rather than giving a general set of criteria for the manifold, then that really leads nowhere. Leads nowhere. That would set up an incredibly complicated, very specific theory that I would have to examine each and every initial condition. So as a blanket assumption, I will make the assumption that basically M naught is overflowing invariant. And I know that, yes, things are getting out in the end. Things are getting out, but at least when I do a backward time analysis, I don't have to be afraid of getting out of the manifold. Now, there's a parallel theory that one could set up for inflowing invariant manifolds, in which case everybody is coming in. Inflowing invariant manifolds are overflowing in backward time. And neither is distinguished over the other one. It's just that I have to settle on one of them. I choose to settle in overflowing invariant manifolds, and you'll see in a second why, but there's an analogous theory for inflowing ones. So this is inflowing invariant if it's overflowing invariant in backward time. So assume that M naught that we're talking about is overflowing invariant. That will be our assumption, but you can change that. Analogous results hold. For inflowing invariant. But once you have assumed that this is the case, what I know practically is that I can take the flow map of this system, which will only depend on one index given the system is autonomous. And when I apply that to M naught, then in backward time, I never leave M naught, okay? So this is always the case for t less than or equal to 0. Incidentally, I could have started with this or once and just assume this. And the minute I know this, I will know that in backward time, the solutions cannot blow up. Because remember, if you're confined to a compact set, then, your solution can be continued forever, given that for any blow up of a solution that otherwise, in a system that otherwise always has local existence and uniqueness, any blow up of the solution is only possible if at a given point that you're approaching, the solution leaves any compact set, okay? Since I made this assumption that the manifold is overflowing invariant, I don't know what happens to the trajectories in forward time. They may blow up, but in backward time, they are confined to the manifold, which is compact, and hence they cannot leave any compact set that I want. They are, in fact, confined to a compact set. So that actually means that in backward time, I can run the flow map in a situation like this forever, because I've already made a pretty strong assumption, okay? So the types of questions that this theory addresses are the natural questions that suppose I've been lucky enough to find such a manifold. then does it persist under modeling errors, uncertainties, and the like, things that I have ignored, chose to ignore, or didn't know about, small corrections to my dynamical systems. So persistence, remind you, is smooth survival. We don't expect this manifold to remain the same as I keep changing the models and refining them, but we expect it to be robust, so that small changes to the model, to the dynamical system, will result in small and smooth changes to the manifold. The other thing is stability. That's also very important because it represents the impact on other trajectories. And that's the reason why we look at invariant manifolds to begin with. And the third thing is that we will be looking into interior structure of the dynamics. Not only on the manifold, but if the manifold is stable, then you expect, in fact, just by analogy with fixed points, to have its own stable manifold. And if and generally it can also have its own unstable manifold. The whole manifold can be of saddle type. And then, unlike in the case of a fixed point, when in the stable manifold you had an obvious target, which is the fixed point itself, all of a sudden you have a variety of targets on a manifold when you have a stable manifold to a manifold. So the question arises, I have all these options and my target is now pretty huge, and my target has its own varied dynamics in general, where am I going to go? So there's all these target asymptotic behaviors that I see, which one am I going to pick? So the internal structure of the stable manifold or the unstable manifold of a manifold in forward and backward time is also important. So interior structure of, if it exists, stable and unstable manifolds of M0. And I could, just speaking, interior structure, I can also worry about the interior structure of the manifold itself, but that turns out to be an easier question because I can just restrict the dynamics to the manifold, my vector field on the manifold, right? Which, excuse me, which has all these trajectories that do their thing, and analyze that. I will say that the current, once you have cleaned up this theory, of course, then much of the actual research then goes on in this area is actually focused on this part, because you have to find these manifolds. You have to know where they are, and that's non-trivial in a general system. We will be looking at examples in which we can see them explicitly, but most of ongoing research is about actually finding them, either half theoretically, but mostly numerically in intelligent ways, not just shooting in the dark. I mean, one thing to appreciate that in a general dynamical system, if you give me a set of initial conditions which is smooth, and I launch trajectories from that immediately gives me an invariant manifold by definition, because I picked a smooth initial curve and I'm launching smooth trajectories from that. I get a smooth surface. So we have an abundance of invariant manifolds in a general dynamical system, yet most of them will not matter that much. Why? Because they just follow the flow, they do funny things, and they curl up, and they certainly won't have this nice property that you can identify, so a carpet within them that is strictly overflowing or inflowing. No, trajectories will do their thing. And also they just develop incredible complexity over time. So the ones that we are really interested in are the ones that don't do that don't give into the flow, and they have a very nice boundary along which you have coordinated behavior, either everybody's coming in, everybody's coming out. And also they have a uniform impact on nearby trajectories, because if you just let trajectories go in randomly, you assemble a manifold, that will not have a uniform impact. Sometimes it will attract nearby trajectories, sometimes repel, sometimes neutral, right? So that's why, even though we have many, many invariant manifolds in a flow, as many as you want, because it depends on your initialization, it's the unified concerted impact of that manifold, kind of resilience and coherence that makes something, one of these manifolds, more important than others. So partly this theorem gives you conditions on the theory that formalizes of what that means, of what you should expect from such a manifold. I wanted to start with an example, and this example is something that, I mean, I came up with this over the years because it has all the issues that one needs to clear up, rather than just going into the way the subject is usually treated. Then people then start writing equations and complicated expressions without too much motivation. And if you're lucky, then you see an example in the end. And this is a very technical subject, but I felt that it's important to see a simple example that shows all the issues. Okay, so this example, I call this example 1. It's actually two-dimensional, because in 2 dimensions we can draw things easily, but it will already go beyond the usual paradigm of just simply stable and unstable manifolds of fixed points. So this example is x dot equals minus x times 1 minus x times 1 plus x, y dot equals simple minus alpha times y. And now we'll be interested in alpha values. So this is, say, a model. Alpha is less than equal to 1, larger than 0. Okay, pretty simple system. Note that the 2 directions completely decouple from each other. What is this? What does this system look like? It's so simple that we can really put together the phase portrait quite fast. So this is the x direction, this is the y direction. All right. What's apparent immediately, what do you do first when you try to understand the system? You look for equilibrium, you look for fixed points. So that means you need to have a vanishing right-hand side for both equations. This right-hand side only vanishes at y equals 0. And on that note, you also notice that, by the way, but it vanishes across the board for y equals 0, which means that this whole axis y equals 0 is invariant. Because if you start with y equals 0, and this equation tells you that you stay with y equals 0, plug that in here. So no matter what happens in the x direction, this is going to be an invariant line. And that's going to be our invariant manifold. All right. So in fact, you know, this is just a preview why, but why would there will be other invariant manifolds. Why do I pick this one? So I don't yet then mark that, but I will sort of give away the target of this investigation immediately. So let's just first do how I would, let's do it by the book, and let's look for fixed points as I indicated. So one fixed point is at 0, 0, right? Because at that point you get 0 for both equations in the right-hand side. So I call that fixed point, I think B naught or something. Other fixed points, well, I can always keep y 0 and fish for zeros of this equation immediately because I factored it. You see that x equals 1 and x equals minus 1, they're both also 0, so therefore they're fixed points. So if this is minus 1 and this is plus 1, I call this equilibrium point A naught and I call this equilibrium point C naught. Okay, those are fixed points. And then what else can I establish? Well, just quickly, because the equations decouple from each other, I've already identified one invariant line, which is here, but there will be other invariant lines that I identify from here. Namely, x equals 0, not only does that lead to a fixed point, but it defines an invariant line, because if x is 0 initially, then x will remain 0 for all times, and no matter what y does, right? So the line I've already drawn here as an axis is actually also an invariant line, but that's not the only one. X equals 1, x equals minus 1. So these two are also invariant lines. So let me draw those in. Well, that's kind of a skeleton already. So all the lines here that you see are invariant lines, not only just because they're coordinate axes, but everything here is invariant to begin with. My last one should go through this one. Okay, and I just read that off the equations. Okay, And next, all right, so I have 3 fixed points, and most likely then these are somehow, they run into the fixed points. So it looks like immediately they must be stable or unstable manifolds. They also could be center manifolds, but they're invariant manifolds associated with that fixed point. Some of which is immediately visible from this equation, because all the vertical lines have decaying linear dynamics on them, right? So that type of thing. And the decay exponents is minus alpha. So I can also draw that. So there you go. That's half of the story already. I can now start looking at individual stabilities. When I look at the origin, the linearization is already there for the origin. So I know what's happening from this direction. The other question is what's happening in this direction, right? Near the origin, you look at the linearization of this vector field, the term when you linearize that comes out is minus x, right? Because all the other terms that you get when you multiply this out and multiply minus x, all the others will be nonlinear. So when you linearize polynomials of x, when you linearize here, you will lose those. So you only have to pay attention to minus x, so which means that you also have decay in this direction. Since you have a one-dimensional dynamical system here, okay, governed by this, we have learned that once you know that you have growth in this direction, then most likely you will have decay in this direction because the right-hand side here changes sign. I mean, you could also have, you know, growth in this direction if you had a double zero here for the right-hand side, but you can easily check that that's not the case. So in fact, the right-hand side does change sign here. If it does change sign here, then you go in this direction, you go in that direction. Okay, so what have we obtained? We obtained, the big picture is that this is a saddle point, right? With an incoming stable manifold, unstable manifold. And what this is a node because it has 2 invariant subspaces. These would be the eigenvectors if I had done a detailed linearization here. And this is how you come in, therefore. The exact shape of how you come in will depend on the ratio of minus alpha, which governs your, governs your decay here, and -1, which governs your decay here. So, you know, if they're equal, then you come in like this. If the decay is stronger in the vertical direction, you come in like that. If the decay is stronger in the horizontal direction, you come in like that. So I'm not going to go into details because I don't know, given the generality that I have for alpha. But either way, it's a node. And I will then have this general shape for the trajectories that I pass here. You know, somehow I come in here. I'm not giving any details because I don't know at this point, but I definitely come in, and other solutions also come in. Well, I'm sort of, let's be consistent. I have to take a stand here because otherwise, let's just assume that I come in here, right? So that means that the decay in the normal direction is faster than in the horizontal direction. I just have to be a little bit specific, and then this comes in. My apologies. This comes in tangent in that case. But remember, I mean, this can also turn into this if the other direction wins, or it can just be turning into a well-defined asymptotic line if these 2 rates are equal, right? But I just had to be specific for the purposes of this picture. All right. So we pretty much know globally the dynamics. I mean, maybe I draw a few more trajectories here so that you get a sense that what happens in this part of the phase space. Okay, and here this just continues. So if this is your dynamics, which we were able to explore with that numerical work, what would you say is important in this picture in terms of global asymptotic behavior? I would say that all trajectories settle down. Now they settle down on this horizontal line one way or another. They don't exactly have the same asymptotic behavior. I mean, this one comes here, this one comes there, right? Or this one here, that goes there. So the details of that asymptotics are different. But if you want a longer term forecast for what happens in this system, then a wonderful opportunity for a reduced order model, which we always seek when we have higher dimensional systems, we'd like to simplify our understanding of the dynamics. A wonderful opportunity would be actually to look at this invariant manifold here, as I already indicated in my preview, like that. Because sooner or later, one way or another, you're really converging to that manifold, and you can then just restrict the dynamical system to this manifold. And the only question will be which incoming trajectory will go where, but you pretty much nailed the asymptotic dynamics. And this example shows you why really also we care about invariant manifolds a lot, because they are wonderful opportunities for rigorous, mathematically defendable reduced order modeling, of which there is very little, I have to say, in practice. People make, guesses, and especially now with machine learning, people don't spend too much time on trying to understand dynamics, but basically shooting in the dark and changing your hyperparameter sensitivity or whatnot, right? Without really understanding the system. But this is sort of crying out for being a reduced order model, what happens on the blue curve. In order for me to be able to discuss this, I have to make it compact. So I'll cut it off somewhere. And you see this is an example in which you see the overflowing invariance, right? So the minute I have to make it compact, then trajectories will be leaving it. So, but that's okay. Hopefully I'll have a theory for this. So M0 is compact overflowing. You can in fact see infinity, even analytic invariant manifold. All right, beautiful. So I'll just say that ideal candidate for carrying reduced order model. Of the full system, because you're running to it exponentially. So after some transients, it's really this dynamics here on the manifold that will determine your behavior, right? Whichever way you go. But I have to cut it off at some point. Excuse me, if I want to have a bounded, compact understanding of what's going on. Okay, so it's as nice as it gets, and we have a good reason why we want to look at this manifold. And let's just take stock and write out whatever we know about this. So the dimension of M0 is 1, and its boundary is not empty. Okay, and I've already said it's compact. I'll just repeat that: compact CR, and R as big as I want. Okay, and even analytic. Sorry for repeating that. So what does it mean, analytic? Remember the distinction between the two. You can have C infinity, which means it has infinitely many derivatives, but analytic means more than that. It means that the Taylor series that you can formally compute for this manifold at any point now will actually converge. Those are two different things, right? So analytic is even nicer than C infinity, which means that its Taylor approximations are very meaningful, even in the limit of n going to infinity. And it's flat. It's also overflowing invariant. And it has a stable manifold. So it has what we call a local stable manifold. So that's not empty. But if I look for an unstable manifold, I find that would be the empty stat. So what would be, just to illustrate, what would be the stable manifold of a manifold? So in this case, locally, this. Okay, and of course then you could say that, well, that's not quite a manifold, because if I define it as I have shown with the endpoints included, then this is like a square, right? And if it's a square, that's not a manifold with boundaries. So this is more of a terminology thing here. You could call it a stable set if you want. But there's also a technicality, because I could, you know, just exclude the boundary here and only talk about the stable manifold of the interior of this manifold. And all of a sudden, you know, I could make it empty and it would look like this. But the reason I still want to name this, even though I have, you know, issues in terms of how exactly I define it to be, if I want to be pedantic and really be able to call it as a manifold, I'd like to point out a feature of this that doesn't exist for fixed points, but it does exist for stable manifolds of invariant manifolds. This is what we call local invariance. We didn't have that notion. We had local stable manifolds, but we said they were, you know, forward invariant or backward invariant. This is locally invariant, which means that if you start on it, you start a trajectory on it, as then it will be staying in the stable manifold and will be converging to the manifold, but it may leave at this point on this entry on one side, okay, which you get by erecting, well, we will call these stable fibers later on, but there's an exit point. So basically you are converging to the manifold as long as you're in this set, but you may leave this set at some point. And this set by itself is not nice in the sense that it's either inflowing or overflowing. It has both behaviors. You come in here and you go out there. But this is typical in higher dimensions, that you don't just have, you know, for the stable and unstable manifold. Remember, fixed point has a stable manifold. You're going to the fixed point for all times, no question there, right? Unstable manifold, you're going to the fixed point, you know, backward time. Things are more subtle when you have a manifold with boundary. Locally invariant is the best you can hope for. So, and again, that would have a more general definition, but so it means trajectories converge to M naught as long as they are in this, this interesting set. Okay. All right, so I'm happy that I found this. I have a reduced order model. In fact, what's my reduced order model? This, because I can just restrict that equation directly to this, and basically tells me your X initial condition is enough for you to predict the fate of your trajectories, because in terms of Y, you will be dying out exponentially fast. That's not an issue. And in terms of where you go, you just need to understand where you go in this one-dimensional system. It's a beautiful setting, right? There you go. Your two-dimensional system reduced it to one-dimensional system. However, then comes the skeptic person and would say, this is only useful for you if what you have obtained is robust. So if I add some small perturbation of things that I have ignored and the whole philosophy, the whole model reduction falls apart, then what good does this M naught do to you? Because it's basically impractical to use it, because surely you have ignored things. So the question would be, is M naught robust on the small perturbations? So this is the question of persistence. And I think we are optimistic about this based on what we know so far, because based on what we know so far, the individual building blocks of M are pretty robust. I mean, a saddle point, that's structurally stable. A node, is structurally stable. Another saddle is structurally stable. This is as smooth as it gets, okay? It's analytic. I had a small perturbation, I had smooth perturbation. The right-hand side is already analytic, and I'm going to add an analytic perturbation. Everything is as nice as it gets, right? And these individual building blocks are structurally stable. So I fully expect, with that knowledge going into this, based on what I've seen in dynamical systems, my intuition would be that then, yeah, I mean, why not? And things are, you know, definitely, these are all robust things. There's no neutral stability here or anything, right? So let's look into that to see whether that intuition is correct. So I will actually add the small perturbation to this. So x dot is equal to minus x times 1 minus x, 1 plus 1, 1 plus x, okay? And let's just add something really simple, even actually linear, because it gets as simple, it doesn't get simpler than that. So I just want to couple also the two equations, because this so far has been embarrassingly simple, the two equations decoupled, but the coupling is nothing outrageous. So epsilon is much less than 1, right? And bigger than or equal to 0. Okay. So what do I know? Well, immediately, you know, I'm on safe grounds because the saddle point here is structurally stable. So I know, just based on nonlinear dynamics 1, that there will be a nearby saddle point. And if the perturbation is small enough, then it will be a small perturbation to this one. And I will have a small perturbation to this one, and this is also structurally stable. So let's write all that out. So the A naught and B naught and C naught are structurally stable because they are hyperbolic. They persist, right? I mean, the only issue is that doesn't seem to be such a major issue, but there was that hesitation that I had here as to how exactly draw these curves, because the details of a node will depend on what alpha is. Once again, if alpha is equal to 1, then your trajectory is the curve, but asymptotically they come in along a line, all of them. So basically, these are the directions that they're tangent to. The reason is that both eigenvalues of the node have then equal strength. So the linearization of the node is just really a bunch of rays. And then depending on the ratio between alpha and -1, I might come in like this, or I might come in like that. So the details of the trajectories of that line will be changing, but there's no question that the equilibrium point survives, right? So they persist as equilibria. It will not be destroyed. In fact, B naught does not move. How do I see that? Because if I do this perturbation and plug in x equals 0, y equals 0, see, it's still a fixed point. So that has to be the continuation of B naught. It never moves, okay, as a fixed point. And I can see that. Now, excuse me. So what will happen to A epsilon, which is one of my saddles, and C epsilon, which is the other saddle? They will have to make this expression 0, even without me getting to this one, right? So suddenly they will have to satisfy the equation. Their coordinates must satisfy y epsilon equals epsilon over alpha x epsilon, right? I just obtained that by looking for their x and y coordinates. If their coordinates are x epsilon, y epsilon, right? So I plug in those and I look for values for x epsilon and y epsilon for which the right-hand side vanishes. And certainly that implies that the second equation must vanish. So when you solve that for 0, this is what you get. So knowing that, I don't even bother solving the second equation for now, because I know it will have to have a solution. for small epsilon. And the reason why I know that is that I know that the fixed points persist. They are hyperbolic. Okay. In fact, we went through this. It's precisely the implicit function theorem will guarantee the local solvability of this equation for epsilon bigger than 0. And that implicit function, what the implicit function theorem needs is a non-singular Jacobian is precisely the one that guarantees the hyperbolicity of the fixed points. Okay, so the two are intertwined. Okay, and I did this calculation. So what do I read off from here? Just sort of in terms of schematics. If this was C naught, and this was the other way around. This was A naught, and this was C naught. So these are the two fixed points here, A naught and C naught. Okay. Look, their new coordinates, which are no longer 0, have to satisfy this relationship. So in the negative x regime, since when epsilon is bigger than 0, and alpha was assumed to be non-negative, this is negative, this is positive. So y epsilon is, excuse me, y epsilon is moving down. It's a negative number, so that the equilibrium will be moving downwards. The opposite is true for C naught, which is here, right? Therefore, it's in the positive x regime. So now x is positive, this is positive, so that will be moving upwards. So there will be somewhere a C epsilon here, and there will be an A epsilon there. Just a little observation. They will also be moving in terms of the y values, right? And x values, and that I can get from here. But for now, for the point I want to make, is just the only thing that's important that this will be somewhere here, and this will be somewhere there. Okay, and this one doesn't change. Okay, so let's worry a little bit about this one. The reason I'm doing this is that I'm trying to piece together what will happen after this perturbation. So let's look at the details of the perturbation. Of the B naught equilibrium point. Okay, and there will be two eigenvalue configurations that I want to worry about, because now I have to be a bit more specific. So when alpha is equal to 1, okay, and what I'm showing here, this is the eigenvalue configuration for that fixed point. Again, I'm talking about this fixed point here. And remember, this is the relevant linearization in the y direction. It's governed by this e to the minus alpha t. When you linearize in the other direction, which you can do here separately, then you get -1. So dk with exponent -1 versus dk with exponent minus alpha. Now, I have assumed here that alpha is 1. So minus alpha is -1. So basically, you have a double root in this case. So what will happen to that double root? We'll see in a second. The other case that I can consider is when alpha is less than 1 and still bigger than 0. Okay. In that case, the eigenvalue configuration is somewhat different because these two roots don't coincide anymore. You have -1 here for one of the roots, and you have minus alpha here for the other roots. So I know that when I perturb things a little bit, they will be moving and they will be staying close. I'm not changing the nature of the eigenvalue configuration substantially. I have two distinct real eigenvalues. But what I do expect here, I mean, here two things can happen. Either they move, split in this direction, or they can also split in this direction. So this was the case for epsilon equals 0. So what happens when epsilon is bigger than 0? I can calculate, because those are the two different scenarios that I showed you. So they either move horizontally or split vertically. I just look at the linearization, x dot, y dot, linearized dynamics. What does it give me? you just have to take the Jacobian of this for epsilon non-zero at xy equals 0. So I trust you can do that, because there will be these are the terms of relevance for that calculation. Okay, these are the only 4 terms, the linear terms, that will appear in the Jacobian. And remember, the only thing to remember is that alpha is now equal to 1, because I'm looking at that singular case. So when you then take those partial derivatives, then it will be minus 1 minus epsilon minus 1 in that case. So you might then recognize, well, this is the standard. So this is the linearization. So this is the standard form, the Jordan canonical form already. I don't have to do much work for an eigenvalue pair, which is of this form. Lambda 1, 2 equals minus 1. So that's the real part. And these are the same 2 numbers with a different sign. So this is plus minus I epsilon, right? So from that, I conclude that what will happen for epsilon bigger than 0 is that they actually split in this direction. And this is for epsilon bigger than 0. Okay, that's the conclusion that I get from this. So what happens for epsilon bigger than 0? The local phase portrait will be a what? A focus, and it's going to be a stable focus because of this sign. You can just check what the direction of the rotation is. So just believe me that, well, don't believe me, but this is one possible. I hopefully didn't miscalculate that. It will not make a difference in the end, but it's this, just to be specific. So it's a stable focus. It looks like that. Okay, and this is just, let me follow up then on this of this side of the story. Okay, so let's just follow all the way through what the global phase portrait will look like for this case when alpha is 1, and then if I run out of time, then I discuss the one next time, or at least I get started on this one. So let's follow up on this case. We already have kind of pieces of all the pieces of the puzzle. Let's go back here. Remember, this is a saddle point. So saddle is structurally stable because the saddle points, I note that here. So the eigenvalue configuration, which I forgot to mention at this point for the saddle, is pretty clear cut, right? So this is the real part of lambda. This is the imaginary part of lambda. And we have, it's a saddle, therefore we have a positive eigenvalue and we have a negative eigenvalue, right? So when you have epsilon bigger than 0, this cannot leave the real axis. So this is what happens for epsilon equals 0. So they are definitely saddles. And their invariant subspaces or manifolds are no longer lines because the invariance of this line and that line is destroyed. When you try to see whether those lines remain invariant, x equals constant or y equals constant, that's not the case. So they will be deforming. So the perturbed phase portrait, which I'm trying to piece together. This is the linear phase portrait near that point, but perturbed phase portrait globally. I'm trying to piece that together. So here was the, the ghost of that manifold, and we had the 2 other here, 3 other here. So what I know now is that I have a saddle point that has sort of moved down, another saddle point that moved up, and I have a surviving point here, which has turned into a stable focus, which is hyperbolic. So the local, we have Hartman-Grobman that tells us that the nonlinear phase portrait also looks like this locally. Okay, so when you piece that together, then the unstable manifold of this saddle point shoots out, right, and then gets influenced by the other one, but that's at focus. So what it will do this. It will spiral into that. Likewise, what was this? This was a unstable manifold for the other saddle point will follow suit and do the same thing. But other than that, you know, they will have their other manifolds. So let me draw the surviving picture here. So this is the surviving saddle. It will do something like that. I was too slow, sorry. And on the other side, it will do something like that. And these are the surviving stable, unstable manifolds, except that I should not use those colors. I should use different colors. So this would be my candidate for continuing that manifold, because this is, to the best of my knowledge, I mean, I also have these, you know, stable manifolds to the saddle sticking in or sticking out of the saddle. But this, to the best of my knowledge, this would be what I could consider as a continuation of M epsilon, because all other trajectories, I mean, look at what they do. So the dynamics within this set is this, okay? And all other trajectories then come in and, you know, do this, or do that, come in here and do that, come in here and do that, do that. So this curve, one way or another, this object is taking up the role of M0, right? In terms of being a target for everybody else. So we could say, great, so that's what I expected, our expectation was right, that it's robust, except there's a big problem. Now, this is really not a manifold. And you could say, all right, but, you know, I made a compromise. And when I said, this is not quite a manifold because of the corners, but, you know, it's still a nice reduced order model when but it's not. It's an infinite spiral. So if you try to then model the dynamics on this as an approximation from what you knew before, right? And you envision some sort of nice graph type continuation of this, to which you can reduce your model approximately, because you will say y is just a nice function of x, which would be the case when you have something like that. So I will just approximate this. I will try to find that function. I will still reduce to that. That won't work, because this is no longer a graph over x. It has this really big problem here, this infinite wrapping, right? This is not a good reduced order modeling. You have destroyed that. There's no nice sheet there into which you could reduce. There's a major problem here. It folds over itself, right? So M epsilon survives, persists, but no smooth persistence. So what that means is that M naught is not even a manifold. Okay, and certainly no reduced order model. Certainly not one from any kind of smooth calculus. So this is the first, such a simple example already tells you that you really have to be careful. Everything is as perfect as you could hope for. Everything is infinitely many times differentiable, analytic. So is the perturbation. You had a nice story that you have a reduced order model, right? And the slightest perturbation, linear, eradicates that. So this shows that we need it. It's more about just the individual smoothness and nicety. There's something more global here at play that you really need to, you know, pay attention to. I work out the other case. We'll see what happens there. And then we'll basically try to see why this is happening, this wrap up. What is it that we should additionally require for this manifold to be robust and hence be a reasonable reduced order, give us a reasonable reduced order model even after perturbation. That's the story for today. Any questions? So we have a homework which is due today. Hopefully you have all the ingredients that you needed for that. And no questions? Then I'll stop the